I know. So what do we think? Tech Talk good? Bad? Suck? Did you see the link I sent today? Okay, so I think. And you saw the link?
I stream live.
Yeah, I saw you guys messaging back and forth. Wasn't that in the 548 channel? You were messaging, why don't you live stream it on Facebook?
I think I need to learn how to use the link.
Yeah, I actually liked the format of this one probably the best. And maybe it has more to do with his story. I just kind of like that idea of him saying, look, I didn't know what I was going to do with my life either when I was in college. I figured I'm going to be a finance guy. And then kind of just telling the story, hey, I ended up working at this small insurance company and worked my way up through the thing. And then that insurance company became a little bit less small, then renamed itself. And now people have heard of it. And, you know, the whole second best place to work at next to Google. I mean, those are all interesting kind of fun things to say. But if you just kind of separate that and just look at it from the perspective of the guy and his path, you know, I think it is interesting to see that you don't always have to start on a single path to get to the same destination, even though sometimes there's easier roads and harder roads. But I thought his story was really cool, and I liked his kind of the conversational. I think it was more engaging than the last one. I don't know that it was necessarily more engaging than the first one, but it was a lot different than the first one. The first one was more about the job, where this one was more about the guy and how he got to where he was. And then I thought it played out really well having Marcus talk and then Jordan talk, so they gave you the different perspectives. But I'm looking forward to having bashing of the company because in 2 weeks we have Maddie and Curcio, Zeman, Brennan, Corey? I think Corey. Anybody else coming? Zamish coming? Just those 5? So these are folks who have gone and worked at Acuity over the last, I guess that would be 3 years, right? So our last 3 years worth of folks are with minus Trey. Trey isn't in the group, but Trey was in the group within the last 3 years. Huh? Yeah, he's an alderman, actually, not a busyman. He's an alderman. It was like a bad Lutheran pastor joke. I should sign me up. Yeah, so it's going to be very interesting hearing them speak. We have to come up with some sort of format for questions and stuff, but hearing them talk about their experience specifically as people coming out of computer science at Concordia and going and working at Acuity. And I'm sure it's not going to be all good because, I mean, one thing I'm going to be very interested in from it is what were the weaknesses? No school does it right all the time, and I know we have a bunch of flaws that we're trying to work on. So it's going to be very interesting to just take that litmus test of, they came out of our program with presumably a good GPA. Usually it's our best students that go and work there. But were they really prepared, or where were they most unprepared? That kind of stuff. And that kind of tells us a story of maybe what aren't we doing in the classroom, but also it tells them a story, or maybe our current students a story of what should you be doing outside of the classroom that benefits you towards that end. So I'm looking forward to that. I think that could be interesting to get the different perspectives. I'm most interested in, I guess, Corey, probably Zach, and Brennan's overall perspective, because I talked to Maddie and Josh Curcio a lot. So I kind of feel like I probably have most of their feedback from those types of things, but I'm interested in seeing what other patterns emerge from the other 3. Okay. Let's see. So let's talk. Huh? Oh, it was terrible. Who told you it was going to be a quiz?
Oh, thank you.
No, you shouldn't let them know. You should have just be silent.
So did Maddie warn you about a quiz? Is that what happened?
Yeah, every single week I'm like, threaten a quiz, everybody study.
Because I warned her earlier about a quiz, but I said Mr. Gonzalez was writing it, so it's probably not worth studying for. Is what it ultimately comes down to. Because anything he writes really has very little to do with any subject.
I know who was writing it. And you left that part out. Sorry.
What's the name of our book? Is that a book?
And one of those days.
No, actually, I have a weird day. My vision actually seems okay, but this eye is twitching a lot. I got like a huh? A who? Blepharospasm? That's an awesome name. I bet you Mr. Gonzalez is going to get a pet named that.
What are you stressed from?
I don't feel like I'm stressed. I feel like I'm all right.
You must be stressed. You're very stressed.
Like, right, I think I'm less stressed now than I was like a week ago. I think I'm kind of getting the hang of things.
Remember when I asked when you're going on vacation?
Yeah, I'm not even looking forward to that vacation. Yeah, she was asking me when I'm going away, so I'm going to Denver. I got to figure out what to do in Denver.
Coding?
Well, yeah, that's why I'll do in the hotel room. I'll code in Denver.
Go to the bunker in that airport.
I mean, I've been to Denver a bunch of times, but we're going to Denver next weekend, and then we're going to Fort Lauderdale, I think 2 weekends after that. And then I'm going on a 2-week cruise over Christmas and New Year's. And then I think we have another cruise in March. That's all that's on the docket right now, but
Why is it cruises?
that's just, my wife and I just do a lot of cruises. I think part of it is just we like such different things. Like I'm all into I'm a hot tub pool type of guy, and then I sit at the wine bar and write software. That's literally vacation for me. So alcohol, coding, hot tubs, and food. She doesn't drink, isn't really food motivated, doesn't go in pools or anything. Just sits and reads. So she likes to go and I'm all indoors. I don't even care what it's like outside. So she goes and finds a nice place in the sun and reads. So cruises tend to just be the nice compatible thing where we can come together for meals. And there's plenty of things to do on the ship.
So you guys could basically vacation at home because you have all of those in your home, and she would, if she only needs a book. So it's just like the being somewhere else.
Well, yes, but we usually go on cruises when it's cold months here.
Oh, okay.
Yeah, so in the middle of December, I'm going to be in 90-degree weather, or say where that's not what it's going to be here. If it was warm here, we wouldn't go anywhere.
Mm-hmm.
But you're right about my side of things, because I could do everything indoors. I just have to survive from my house to wherever I'm going where the hot tubs are, which is in my garage. So,
Yeah.
but yeah, you're right. But we need to figure out what to do in Denver. We've been to Denver several times. Well, so Denver the problem is it's all about like hiking and things like that. And we don't, my wife and I aren't into that stuff. She likes mountains and things like that. So last time we were there, we went driving and we went, driving. She had me drive her to like where the trees have leaves that change color. Yeah. We drove 2 hours to see a tree that was a different color. That doesn't make any sense.
That's romantic.
That was 2 hours each way.
They have those.
Your wife. They have those natural hot tubs.
The natural springs. I looked at that. I asked her if she was interested. She's not.
So
But she doesn't go in pools and hot tubs and things like that. So she wouldn't have anything to do there. And she won't drive on the mountain cliff thing, so
What about laser light shows?
she'll watch laser light shows.
They have those.
Like, is there like a special one?
There's an entry to Beyond laser light show and guided meditation.
Oh.
Looks like it's a Halloween themed one.
Oh, is that at Red Rocks?
I have no idea.
There's this famous place there called Red Rocks that so I don't know. We'll figure something out. What was I doing? Oh, Zybooks.
There's a concert place called Red Rock.
Yeah.
The departure point is the International Church of Cannabis.
For the light show? Wonder if there's even a light show. Okay, so this is us, right? And then what chapter were we? 5? That's what we were doing for homework today, or this is what we read today for today? We did compiler stuff, right? But I only gave you homework from assignments, right?
Yes.
Oh man, we got a whole compile. Okay, we gotta get cooking. All right, so but 5 was what you read, and where did things get crazy?
7.
All of them.
All of them? Okay, let's
That's
just.
the first one.
All right. Well, let me just run through this real quick and point out things that are kind of interesting, and then we'll skip the rest. Yeah. So logic gates, and, ors, and nots. So this is an inverter. We understand truth tables, what those guys are. So all that stuff made reasonable sense. So an and, both, if A and B are both true, the output will be true. So only when both are 1s is the output a 1. Otherwise, it's always a 0. With an or, it's only a 0 when both are 0s. So it's the alternate, and a not is an inverter. Flips what the other thing is. And then you can use combinational. This whole idea of combinational circuits is building crap with those things connected. Put those things in combination together, and you get interesting hardware-based formulas where you feed something into one side, you have these inputs, and those inputs fly through and ultimately give you an output. All right. Blah, blah, blah.
Was anybody able to get that last activity? Because I couldn't figure it out.
Yeah, you have to drag the little endpoint.
Does this say click to add?
I dare you to try it.
What am I supposed to do?
Okay, click start, and then you click on it. Don't click and
Don't
drag.
tell them, Maddie. Just let them figure it out.
Well, I mean, hold on, let me find. Convert the equation to a circuit.
That one was,
So Z equals B plus A. So here is, so plus in this case is it an and in the way they're describing, or is it an or?
Oh.
It's an
Don't
or.
tell 'em.
Well, I was going to scroll up. This is just the plus. All right, so B plus A. So the output, we're going to be dealing with an or here, right? Oh, I click it. Oh, too many clicks. Do I undo? Do I have to drag this guy? Okay, and it's A or B. So I got to drag from.
Oh my gosh, what is that? I've never seen that before. What is this magic? That's what I was doing too.
I started with that, and then I clicked run or whatever, check.
I
And
just
then
did
it's
that.
like,
Ah!
After like an hour, I'm just like, heck with this. I don't even know.
that's when you message
All right, do I have to do any more? Or am I good?
No,
No,
you're good.
all right.
Those were magic lines appearing. Ridiculous. I'm leaving.
Oh man. All right, decoders,
Oh, that was confusing.
multiplexers, and adders. Okay, well the
it's a muxer or whatever.
multiplexers, multiplexers. So here's the deal. Decoders and multiplexers. A multiplexer takes a whole bunch of inputs, squeezes it down to one output. A decoder takes one input, splits it into multiple outputs. All right, so if we think about this from a network perspective, which is maybe sometimes the easiest way to think about it, let's say that we have 2 buildings on campus. So we have, well, kind of our campus is weird here because we have like one main building, but then we have a couple of buildings that are off. So like the environmental center,
I don't know.
there. Okay, so the environmental center is not directly connected to this building. So when they built that guy, they would have like dug a trench or something like that and ran a single wire, probably a bunch of wires. Let's just say it's a single wire that went from this building to that building. But now once it gets over there, it's serving that building over there with all the services, all the various networks that we have over here. So somewhere we had to take all of our services here, compress it down into a single transport. So that would have been a multiplexer that took a bunch of inputs, turned it into a single output across under the parking lot or whatever. And then a decoder on the other side, something like that, would have taken that input and split it back into its all the wires that would have been on this side. So you only had to have one thing going across. All right, so that's what these two guys are. An adder is a whole different animal. Okay, but the decoders and the multiplexers, what's this? A 4x1 mux. So yeah, so a 4x mux is a shorthand for multiplexer. So we have 4 inputs here, and it's going to compress it down to 1 output. Okay, and notice they do it kind of like a truth table. So for our 4 inputs, we will have 2 bits for our switch. All right, so this is our switch. So here are the 4 pop. Did that flicker?
No.
Oh, I don't know. I just saw the. Yeah, that just happened again. Oh, it's that guy.
Oh my gosh, that scared the crap out of me. You seeing things.
It's like, shut up and let me finish. Let's go a whole class like that. Because every now and then you just get off of me.
Oh my gosh, I would be screaming. Like, right.
So now it's a cry wolf problem. So if that actually happens at some point, you guys are going to be kidding.
Yeah, right.
That was like the most squirrel moment ever.
I saw a flicker. Well, actually, the reason I was looking for the flickers is I just got, this is a new HDMI converter. And because my other one had kind of busted. But the one before that had a flickering problem where the screen would go on. Actually, we had that in here, didn't we, the first class? Yeah, so when I saw the change, I think, oh, is it flickering again? Is this new one not going to work? All right. What was I talking about? Oh, yeah. So when we have 4, we need to be able to uniquely identify 4 different inputs. So we do that with a 2-bit switch. So for 4 different inputs, we can use 2 bits to represent 0 through 3. So in the 0 state, I0, this guy fires through. In the 1 state, I1, this guy fires through. In the 2 state, I2, this guy fires through. In the 3 state, I3, this guy fires through. So based on what inputs you apply here, so we would have 4 things constantly connected to this multiplexer. And then depending on what we fed to these 2 switches, that would determine which of these lines gets hooked up. Does that make sense? So that's what a multiplexer does. You want to do it again?
No. Just let it simmer a little bit.
Okay. Well, let me give you a little context. So let's say, actually, let me give you a real live context for this. So we're looking at doing a switch thing over here so that all the different TVs come on. So when I plug this in, you would see it here, and you would see it on these side panels and that kind of stuff. And I have no idea why there's a TV in the back of the room, but whatever.
If you're lecturing.
Lecturing to who?
To your class.
So what screen you have pulled up?
That's
You
like
get
what
the
they do.
laptop.
That's like what they do in churches. They have it in the back.
Oh,
so that
he needs a script.
Oh, you mean like for that's my what I'm reading from?
not necessarily like in church. It's the same on both. So it's not.
Well, so that's for me, that TV?
Yeah.
What am I supposed to see on there?
So then if you're instead of like staring at the screen and reading
So
off your
don't
screen
know
that
how
way.
to do it.
Oh. So since I mean, for me, I'm sitting here staring at my laptop, but if I was lecturing in the front and I was running a slideshow off of that, I would see my slides there rather than have to do that. It kind of makes some sense. Yeah.
Yeah.
That's not the way you roll.
Well, see, I got, what's this thing called again, Jordan? Blephro. Blethro. Blepharospasm. I have a blepharospasm today. So that's why I didn't understand what that was for. What I got going on? So anyways, we're going to put a switch box up here where we have, let's say you have 4 different inputs. This is one computer, this is another computer, this is another computer, this is another computer. And we have 1 TV, so it's a little bit backwards from this. So let's say we have this single TV here, but we have 4 different setups. So maybe 3 laptops here and this desktop computer. And we only want one of those to actually connect to this TV at a time. So if this is laptop 0 over here, I would hit the switch and it would feed it a 0 and a 0, and that would make sure that only computer 0 was connected to this output, and that's what's hooked into the TV. So it's a switcher that allows me to have 4 different things in this case, and me choose which individual thing lets its signal go through. So these other 3 had HDMI plugged into them, but we're not going to let them get to this TV because we've done the switcher to only show 0. So we fed, a little switch box has a little thing like that. That's probably feeding a 0, 0 or a 0, 1 or a 1, 0 or a 1, 1 to the 4 different options. And this multiplexer, this switcher, will make sure that the right HDMI connection gets made. So the right laptop shows up on the screen. So that's kind of the idea of a multiplexer. And maybe a switcher is a better way of thinking about it. You can have a bunch of inputs here, but only one of them is going to get its message across. And the message that gets put across there is going to depend on which code you put in here that kind of dictates 0, 1, 2, 3. If you want to have more than 4 inputs, then you're going to have more than 2 bits. So if you had 3 bits, 3 bits lets us have, did that really not flicker again? It is that thing. We got to turn that off. Why are you going all the way up here? Oh, you turn it off from up there?
Yeah.
Oh, there's not just a power button on it?
Now it's breaking.
Now there is somebody over here. All right. See, it's the blepharospasm. Yeah, my blepharospasm is acting up. All right. So in any case, if we wanted to have, if we had 3 bits down here, 3 bits for input, that means I could have up to 8 inputs. So I could have a 4 by 1, or I'm sorry, an 8 by 1 multiplexer would require 3 bits for inputs, because I would need 3 bits to uniquely identify 8. Now I might not need 8, so I might only hook up 5. But if I have more than 4 things I need to switch, and I have less than or equal to 8 things I need to switch, I would go to an 8 by 1 multiplexer, because multiplexers always go down to a 1. All right? So, but I would need 3 bits, because we see here that 2 bits only allows me to uniquely identify 4 states. 3 bits would allow me to uniquely identify 8 states. 4 bits would allow me to uniquely identify 16 states, 0 to 15. Make sense? So depending on how many things we want to switch between, we would need to get a bigger multiplexer, and the bigger the multiplexer, the more bits we need for the switch. All right, questions on that? All right, so these guys are actually pretty powerful. They're heavily used inside of processors. We're going to see that, I'm guessing, later on, that they do an MIPS architecture somewhere. Because you can imagine pretty often, heck, even if you just think about our little MIPS processor, we had, 7, 8, 9 different instructions. So depending on which instruction we were working with, a different circuit would fire, right? Each one of our instructions had a little program associated with it, an algorithm associated with it. So we would, depending on the instruction that came in, we would hit the right switches here, which would fire the right instruction for its inputs and all that stuff. So it allows us to switch between which instruction the user asked for. All right, so got that crap. So here's a decoder. So a decoder takes, here's a 2x4 decoder. So this guy says, here's my 2 inputs, and this is which output fires as a result of that decoder.
Is there any rhyme or reason to how you would determine, like if you look at that little graph thing?
This over here?
Yeah.
Yeah, so notice the 2 bits. These guys are always just counting. This is 0, this is 1, this is 2, this is 3. So these are the 4 unique states that can be
Right. I get that, but
represented by
how did-
this.
How did they determine where to put the 1?
Well, what do you mean? Where to put the 1?
You see how it's like under, there's only one.
Oh, over here?
On the right side, yeah.
Oh, yeah, because this is a 1, this is a 2. So we could have actually had more states than this represented by them, but basically,
Oh, so it's like in binary?
yeah. So if this is
Like it's
no,
like
so
a number, though.
yeah, so here this is over here is a number. So this is the number 0, the number 1, the number 2, the number 3. But rather than thinking about them as numbers, think about this as 4 unique representations of 2 bits. So
Yeah,
so
that's
these
how
are
I'm
each 2
thinking of
bits.
it. I'm not thinking of
Yeah,
it.
so forget about the right side for a second. Over on the left side here, we have 2 bits put together in every permutation possible, right? We have 4 unique ways of putting 2 bits next to each other. It just happens to be the number 0, 1, 2, and 3. Okay? So we have 4 unique representations here. We just happen to have 4 outputs here. If we had 3 bits here, we can have 8 outputs here. Up to 8. We don't have to use all 8, but we can have up to 8. All right, so since we have 4 representations here, we're choosing that this first representation, 0, 0, would fire on the Y0. So 1 is a true, 0 is a false. So signal's not getting through, signal's not getting through, signal's not getting through, this one does. This one fires on Y1. This one fires on Y2. This one fires on Y3. So all of them fire on exactly one of the outputs and have zeros every place else. So somewhere inside here, we have to imagine, so this decoder is going to be made up, it's a combinational circuit. So inside of there is going to be and or and not gates and things like that. So what's firing on these, so this is going to be a 0 and a 0 and a 0 and a 1 firing into some circuit that's in here that magically will have the correct output based on how all that stuff's wired together, because it's representing the right function. This is kind of related to that function from the previous screen that Ani couldn't figure out. So you get what I'm saying? So that we would figure out the mathematical function that is the, given these 2 inputs, how do these, what and or and not gates do I need to put together that ultimately when I feed this stuff through will give me these exact outputs. This is effectively the truth table for this decoder. And if we popped open this black box here inside, we find AND gates, OR gates, things like that. And that ultimately equals some formula that when we fire a 1 and a 1, we have a 1 come out on the X3, so on and so forth. All right, that makes sense? Know how that guy's working? And maybe just to say one more thing about this, I'm referring to this as 4 unique representations of 2 bits, but the best way to get 4 unique representations of 2 bits is just to count in 2-bit binary. 0, 1, 2, 3. 4 unique representations of 2 bits. If I said, give me all the unique permutations of 3 bits, you would count 0 to 7.
That would have helped a lot with logic class.
So you're saying that computer science would have helped in a logic class? Bit counting? Or are you talking about the unique permutations?
Yeah, I mean, like, I know the unique permutations, but I never thought about it in the binary way.
Oh, that counting gives you the unique permutations.
Yeah.
So you were like trying to just memorize bits next to each other?
It's not that hard to, it's not even memorizing.
What if I said, give me all the unique permutations of 64 bits? Memorize that. What you do is you go and write a program to give you every unique permutation of 64 bits.
Lots of light bulbs.
Good. You like light bulbs. I'm getting tons of light bulbs in this eye. With my blepharospasm.
It's only been 10 minutes.
I'm old. I don't remember anything anymore. So this is empty husk up here. Did we talk?
Remember all of this?
Oh, this is easy stuff.
How many pages?
That is kind of funny.
He just invented it.
It is kind of, this is the first time I've looked at this too. It is kind of funny though, the things that some of us remember. Well, goes back to the whole 10,000 hour thing, right? I spent huge chunks of my life doing this stuff.
I don't think you talked to this.
Really? I didn't do the 10,000 hour thing in here?
I don't think.
You've heard this before, right? Just you spend 10,000 hours on anything to become an expert at it.
Is that proven?
Yeah, it's something like that. It's related to this book that I've been reading. I was telling Maddie about it called Outliers, but it's something I've heard for years. You know, that the idea is that if you want to become an expert at anything, you have to put 10,000 hours, let's say, of practice in. And typically, you know, there is a direct correlation between effort, practice put into something, and how good you become at it. Natural talent plays a role, you know, so I mean, if you just are naturally not, if you're not a ninja, probably aren't going to do fleet-footed type stuff, right? But, you know, if you have some sort of talent in an area and then you put a lot of effort behind it, you will likely become better at it than somebody who might have more base talent than you but didn't put as much time in. Mm-hmm. So it's this idea of 10,000 hours to become an expert at something. And nobody actually keeps track of it, right? But, you know, if there's something you're really passionate about, you tend to just spend a lot of time doing it. So I don't know how many hours I've spent doing this stuff, but I would presume it's been over 10,000 at some level. What?
My coworker and I did the math, and it's like, how long would you have to work that job to be an expert in what you're doing?
For like a normal job?
Yeah, like if you did your typical 40 hours a week kind of thing.
Yeah, see, I don't know that would work. I think you'd have diminishing returns because I think it has to be more compressed than that, in my opinion.
What do you mean?
Well, so like for instance, if you really wanted to become an expert at something, I don't know that working 8 hours a day at a normal job is like focused work. Because if you think about what your normal day is at a job, you aren't necessarily focused on something very specific. You might be answering emails or doing all this other stuff. So it's not just constant practice.
Okay. I guess you can build in extra hours.
Yeah, whatever. Yeah.
Still.
But what was it?
I think it was like 5 years.
Oh, really? Yeah, so I mean, that can't be right because I mean, that means anybody who's been working at, you know, a company for 5 years should be an expert at everything that company has and
No, because that goes back to
expert in their job at that company, which I think is also not true. I mean, there's plenty of people that have been in a job for 20 years that don't know what they're doing. So I think that's why I'm kind of saying I think it needs to be more focused work. Okay. But yeah, so that's the idea. So it's funny of what things we remember and what things we don't. You know, so I've done this stuff a bunch. I haven't actually taught this stuff in a while, but at some point it's in there, so I just have to kick off the dust. But, you know, other things that might seem like common knowledge to somebody, if I haven't dealt with it in a while or something like that, it's just gone. I have nothing. That's the empty husk thing. All right, so that's decoder. All right, so now we have adders. So again, maybe this will make more sense now that we've been talking about things in terms of a number of bits. So if we have a 3-bit adder, that's adding one 3-bit value to another 3-bit value. Now, what's the biggest 3-bit value? So we can have a 7, right? So I can have 111, that's a 7. And my other biggest 3-bit value would be another 7. 7 plus 7 is 14. How do you represent 14? How many bits do you need to represent a 14? 4 bits. But notice a 3-bit adder only has 3-bit output. So that means that if I put in a 111 here and a 111 here, I would get a 000. Because I'd have a carry. If we're adding. That's what this is. This is an adder. Yeah, so that's this guy is an adder. So what an adder does is it takes this stuff, this 3-bit number, and adds it to this 3-bit number. Inside this black box here is going to be a combinational circuit, bunch of ands and ors and NOTs and NORs, and I don't think the book talked about NOR gates and things like that, or NAND gates. And so we have these other gates, like a NOT AND and a NOT OR. So a lot of our modern electronics are actually built in terms of NAND gates heavily, because companies, what they'll do is they'll buy them in bulk, so they get a lower ultimate price for a NAND gate, and then they just make their logic work with more NAND gates if they don't have to get down to some sort of micro solution. So typically what we see is when you look at electronics, really, really small compact electronics tend to be more expensive than not necessarily large, but less purposely compact electronics, because they probably used cheaper parts, not necessarily worse parts, but more cheaper parts. So they used 300 NAND gates instead of 100 of the correct gates, something like that, let's say. Most of our stuff today is all printed circuit boards anyway, so this kind of goes out the window, but it's but that's still an example. Yeah. All right, so yeah, so inside of this square here is a combinational circuit like they introduced at the beginning of this chapter. So there's going to be AND gates, OR gates, blah, 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 all this stuff in here that ultimately accomplishes the job of adding, the formula of adding 2 bits together, right? And then you have a whole bunch of things you can add 3 bits together. Well, 3 pairs of 2 bits together, ultimately giving you a 3-bit output. Now, some adders will also have another output for like a carry bit. So when we actually talk about the chips, we have full adders and we have half adders. Typically, full adders will have a 4th output that is a carry, because you can kind of stack adders onto each other to give yourself like a super adder. If you want to add 6-bit number, you can use 2 3-bit adders with a carry. That kind of stuff. Okay, but that's what an adder does. Adds numbers. Cool? All right, so that's what that guy is. Okay. Oh, timing diagrams. Okay, so this is going to deal with, when you think about circuits, we're thinking about electricity flowing through something, right? And if we're looking at a pattern of how something might work, because the book talked about analog versus digital. Maybe it's in this chapter, actually. Analog versus digital in here? Oh, whatever. Analog, anybody know what the difference between an analog and a digital signal is? Did it really not talk about analog versus digital? Oh, it's in there somewhere. All right, hold on. I don't believe any of you people. It's got to be in there. There's just no way it didn't talk about analog versus digital.
Oh,
Line 1. You'll lend me. All right, so.
like 2 sentences.
No, I think it talked about it forever.
No, it did not. No, it was the electric
Timing there. Okay, so analog. This, if you want like a real life example of this, how many of you have ever had a TV where you had the rabbit ears for getting the the signal in? And sometimes you could have half a station, right? Like you could sort of watch the game or sort of watch your show. Okay, now how many of you have like a digital cable or digital DirecTV, Dish Network, something like that? Have you ever had half a station? No, you don't get half stations. It's either on or it's off. Okay, sometimes when the rainstorm hits your satellite, you'll start seeing the color blocks, and then all of a sudden, boom, gone. Okay, when you have no signal, because analog, you're measuring, it's not 0 or 1, it's 0 or 0.1 or 0.2 or 0.3. You have all sorts of measurements in between. Okay, it's a fluid sign, whereas digital is off or on. Off, on, nothing in between. So if it's either not on or it's on, you don't have sort of on. All right. Computers are digital, 0s and 1s. Okay. This is why back in the old days, Remember, how many of you ever used dial-up internet? Okay. All right, so okay, so we'll have a contest. Your best impression of a dial-up modem.
The
I remember that.
I'm pretty sure I'm the winner. Right? I maybe heard dial-up modems a couple times more than you did. 10,000 hours of practice. I got two things. Anything computer science and that. Those are my two talents. What's all that noise? When you say dial-up, what were we doing? We were connecting to another server. All right, we're going to have some more light bulbs go off here. What class is that?
Mr. Gonzalez.
Oh, yeah. Mr. Gonzalez was using GitHub earlier. And then somebody forked his repository, but we won't get into that. Huh?
You're now teaching people how to use GitHub besides just pushing stuff?
Yeah.
That's awesome.
I know.
Congratulations to whoever those undergrads are. Or was that, yeah, that is undergrads.
Those are first semester sophomores.
Dang it.
470?
No, that was not 470.
Yeah,
That was 250.
It said 470.
Well, if it said 470, then I was putting it in the wrong slide set.
Oh.
Yeah, and I was putting it in the wrong slide set. I'm just going to quickly.
Forget.
Here's the history of forking. Yeah.
All those jokes.
Do we know those jokes in here?
No.
Have you heard of GitHub? Who in here has never heard of Git or GitHub? Well, you used GitHub all last semester in 518, right? And I had you fork the repository in there. Where that came from is an old C system call called fork. And what fork does is it creates a clone of a running process. So you fork a child process. So you can imagine how, with techies in a conversation, things can start getting giggly pretty quick. And years ago, the story I always tell related to that is I was in, this is when I was a Unix sysadmin at Western Illinois University. I was sitting at the table with some other developers, and we were talking about this program we were working on called the Reaper. So I had written this program called the Reaper that would reap, like you've heard the Grim Reaper comes and picks up the dead, right? So it would reap dead children. So we would fork new children and then reap the dead ones. So we're having this conversation at like this breakfast place. And these old ladies behind us are not happy because they have no idea what we're talking about. We're over here talking about forking children. So hilarity ensued, I guess.
How did you explain that one? Or did they just walk out?
They just walked out and gave us a mean-looking face. Okay, I got all of them. Copy that. Yeah, so this was actually the 250 class I was teaching today. All right. Oh, we both slide sets. All right, so we're opening our slide set. What was I talking about? Dial-up modems. Okay. So what problem is a dial-up modem actually solving? So we have our PC, and our PC is digital, right? And then we have, we'll call this guy the internet server, whatever that means. The guy who's giving us the internet. So he's also digital. This is another computer. All right, now, probably playing video games in there. All right, so this is telephone. Have you heard of POTS networks before?
I have an idea of this.
Plain old telephone service is what
Oh,
POTS is.
plan.
Really?
Yep. All right. So basically, you have a computer that lives somewhere else, not at your house. You have your computer that lives at your house. Between you and that is a POTS network, copper wires, analog. So we got a problem. I need to talk between digital devices using an analog cable. And of course, modems would be green, right? So we used modems on each of those. Modem stands for modulator, demodulator. It converts between digital and analog, and from analog back to digital. All right, now, having said that, how many of you have seen that before, TCP/IP? Do you know what that is?
Protocol.
It's a protocol. Specifically, what does TCP/IP do? See, this is the problem with education today. This is like the most common protocol, right?
It's a
Yeah.
transport protocol.
Transport control protocol over IP, over internet protocol. But what's his job? That's a fancy schmancy name, TCP/IP. And you just told me what it stands for, but what is his job? His job is vital.
It's a one-way way to transport bytes.
I think it's a
What is his very specific job? He solves one problem
handshake.
that is absolutely vital.
Send messages.
Okay, tell me more.
So he sends one bit after other,
Okay.
which can be read.
What if something goes wrong? What if somebody's standing over the cable with a magnet and there's corruption to the data?
So is it handshake?
It's not related to handshaking. The other thing we're going to talk about is.
But I understand what you mean. If it's wrong, it's kind of a retry.
It's retry, yeah.
Until it's confirmed.
TCP/IP manages the sending of messages and guarantees they arrive in the right order. So it will retry in the event of corruption. Okay. So what TCP/IP does is it says if you send something from one computer to another, it will get there eventually. That eventually might be longer than you're willing to wait, but it'll get there. So TCP/IP manages the guarantee of data leaving one place and arriving at another place. But dial-up was before TCP/IP. So all that beeping and things like that, Blade just mentioned something called handshaking. Here, I'll just put it on the next screen. So handshaking, all the beeping and stuff. The two computers are negotiating. Now, because one interesting thing here is you would, so what speed modems do we have? Most of you who did dial-up probably did it on a 56K modem. Anybody have like a 28.8 modem, 33.6 modem, 14.4? My first modem was a 300 baud modem. That's bits per second, 300 bits per second modem. Not a lot, as opposed to 56,000 bits per second for a 56K modem.
Yeah, my first one would be 56
Mhm.
kilo.
Yep.
bits.
Yeah, 56 kilobits or 56 times 1024. Yeah. So in any case, did you ever notice that even if you had a 56K modem, you didn't always connect at 56K, and in fact, you probably rarely connected at 56K.
5K.
You would connect at like 53K or 48K,
Maximum.
sometimes lower, 37.5, sometimes something like that. Some number that was less than what your modem said you were supposed to connect at, right? Okay. Now, one thing is you could only connect as fast as the slower of the two modems. So in our picture here, whichever of these two modems is slower, that's the maximum speed you can talk. Okay? But if both of these are 56K modems, let's say, you still might connect at something substantially less than 56 kilobits per second. Okay? Why? That handshaking, all that beeping stuff, these two computers are negotiating with each other. What are they talking about? What is the fastest we can talk without screwing up? No TCP/IP. We don't have error correction. We don't have TCP/IP to back us up if a bit gets corrupted. So they had to figure out what is the fastest that we can talk over this analog copper wire so that we don't mess up. Because nobody's got our back if we mess up. It's corrupt. Does that make sense? So all that beeping and buzzing and all that stuff is those two sides negotiating on the fastest speed that they can talk without messing up. That's the story of all the beeping and stuff. And that's called handshaking. So now you know how the internet was born. How did we have our computer talk to another computer over a network that didn't speak the same language that we spoke, that the computer spoke? We used digital signals on the computer, ons and offs. In between was analog signals. Okay, but now what's interesting is how many of you have AT&T internet at your house? Only one person. Okay. Okay. So do you know what kind of internet you have with AT&T?
No.
All right, so AT&T would be a type of internet called DSL, digital subscriber line. Now, so this is a digital subscriber line, and chances are, if you went out to AT&T's website right now and you looked at what their internet offerings are, not paying attention to fiber, because fiber is like the next gen of this, a whole new technology. But DSL, the maximum speed you could probably get is like 24 megabits per second, but typically they're going to probably sell in like 12 and 18 megabits per second because this 75 not over DSL. So you might have, if you know you have 75 megabits per second, where's home? What?
Oh, St. Louis, Missouri.
Okay, well, so you're in a big market, so it's possible you guys have fiber.
We don't.
You don't have fiber? Okay, then it's not DSL. Are you sure it's AT&T that has your internet?
100%.
Well, there's no way it's 75 over DSL, so maybe they must be doing something different there. Because AT&T does have fiber. Like they have fiber in downtown Milwaukee that goes up to a gigabit, and they can do slower speeds. But DSL, the fastest DSL can go is 24 megabits per second.
I know we don't have fiber.
Okay. Well, whatever. I have to look at it closer. But 75 sounds like really crappy cable modem service to me, or the dirt cheap fiber if you're on AT&T's fiber network, because what they talk about on their fiber network is gigabit internet, 1,024 megabits per second. But that's going to be more expensive, but they might sell like this budget pleaser $15 a month for 75 megabits per second over fiber or something like that. It's possible. But DSL wouldn't be able to communicate at that speed. It's just not part of the technology is not capable of it. So DSL, let's call it max 24 megabits per second, where if you are around here, you have Spectrum, or who is it now? Yeah, Spectrum, right? So Spectrum, so this is the fastest, actually it's 24 megabits per second. This is their fastest they offer. Spectrum around here offers so their budget pleaser internet has a max of 200 megabits per second. Spectrum won't sell you slower internet than that. They might have like some sort of like free internet or something for low-income families or something where they would sell you less, or give you less. But 200 megabits per second is the slowest that Spectrum will sell you in this market. It used to be 100, they doubled it last year. So if you were,
We have 120.
you have 120,
Yeah.
that's actually a weird number from Spectrum too.
Yeah, I know.
They sold it to you as 120, or that you just tested it at 120? Okay, yeah. So you probably, well, you might have 200 that's only going at 120 because this is maximum speed. You're still at the mercy of who you're downloading from.
Right.
Yeah, so if you're downloading off somebody's dial-up modem, you're not getting more than 5K, 5 kilobits per second. But this is the maximum theoretical speed of the pipe. So if you're in the market for internet here and you're looking at between AT&T and Spectrum, the fastest AT&T will sell you is 24 megabits per second. The slowest Spectrum will sell you is 200 megabits per second. As a human being just looking at that, which do you want? Because chances are this is cheaper than this. So what AT&T does to get you in, so we're going to go ahead and predict you either have UVerse or DirecTV at your house as well, not just AT&T internet. UVerse, yep. So UVerse is an AT&T television thing. Do you also have AT&T cell phones?
Mm-hmm.
Okay, so they've bundled all their stuff together in order to drop the price of it where their internet is probably almost free on top of the rest of their bundle, which then says, oh, well, do you have 24 megabits per second? 18, yeah. So, which effectively makes that an okay deal because they're not really paying for the internet. It came with everything else. But if you were paying for it and this was $60 a month and this was $60 a month, you want 200 megabits per second instead of 24 or 18 or whatever. So in any case, this guy is all fiber. It's over coaxial cables. That's why the speed is so much faster. So this really has nothing to do with our POTS network thing that we're talking about here. So if I dump the Spectrum thing here for a second, well, I'll leave it in there in case you want it for your notes. But this is what we're really dealing with is DSL uses POTS for its connection, but its name is digital subscriber line. So this is effectively digital over copper, as opposed to dial-up modems did analog over copper and required modems to modulate and demodulate. Okay. Now, where they really mess with the consumer is when the dude came to Ani's place and set up that internet, they said, here's your DSL modem, didn't they? It's not a modem. No modulating, demodulating needed. It's digital at the computer, it's digital over the copper line, it's digital on the other end. You don't need a modem. You just need a guy that knows how to, initially, it's kind of a hardware-based TCP/IP that can put a digital signal over the copper. So it's not a modem, it's something else. They just figured people were already used to the name modem. Same thing's true for cable.
I think it's just because people think that modem equals terminal.
Modem equals internet
Yeah.
is what it comes down to. Modem equals internet. Because if you have cable internet at home, you also have a cable modem. That's not doing modem stuff either.
But the modem is actually a abbreviation of the.
Yeah, modulator, demodulator. All right, so DSL uses that plain old telephone service to give you a connection. And with DSL, we had something called, we're going to say, suffers from the final mile. Do I want to call it final mile syndrome? Let's call it that. Kind of now it's like the final 3 mile, but it used to be when the very early days of DSL, you had to be close enough to the home office, where the home telephone company, in order to get DSL. And there was legitimately a point in every town where your neighbor might be able to have DSL and you can't, because you were just slightly too far away. So you had to be within, as far as the wire is laid, a mile of the source. The way they started getting that out farther is they had these things called D-slams, remote D-slams, where they would put one a mile away from the company, then put another one a mile away from that, and another one a mile away from that, and they string them together until they decide, yeah, we can't sell to these people out here anymore. But now it's kind of the final 3 mile. The technology's gotten a little bit better, and but still, you need to be in reasonable proximity to the home office or the closest D-slam. Now, what possibly happened is when, and we'll even make a prediction. So when you bought your 18, did you actually buy 18 or did you buy 24 and they came out and said the best we can do is 18?
They actually they threw something even less than 18 and then we upgraded.
Okay. Because sometimes what will happen with DSL is, you go to AT&T site and you say, oh, well, here's my address, and they say, oh, we can offer you up to 24 megabit internet. And then you sign up for that, they come out to install it, and they can't get a connection at 24. They can get a connection to 18 because you're just a little bit too far away to get the 24. So sometimes you have that issue with DSL where you wouldn't have that issue with cable. But DSL is a dedicated line. So if you got 24 megabits per second, and that's you're subscribed at that speed, that's all your 24 megabits. You're not sharing with anybody. Cable modems are a shared technology. So 200 megabits per second, you're actually sharing with everybody in your neighborhood, let's say. That used to be a problem because we didn't have that much bandwidth to go around. So you used to have this issue where if all your neighbors were downloading things, you would get a slower speed than you thought you should get. But now, really, 200 megabits get you 200 megabits as long as the source you're downloading from can support it. And it's even worse on the other side. So for a long time, the DSL providers like Verizon and AT&T, they would say, well, ours is guaranteed bandwidth, where the cable providers, that's shared. So you don't necessarily get what you're paying for. But then the DSL providers, they would do they would take the airline and the hotel strategy for selling bandwidth. They would oversell the seats in the airplane or oversell the rooms in the hotel. So they might have, let's say they had a total of 1,000 megabits of internet to sell. That was their total bandwidth. They might sell 2,000 megabits in, let's just say, 10 megabit per second DSL contracts. And just hope that everybody doesn't try to use it at the same time. Because even though we've promised them they have all that bandwidth, we don't have enough bandwidth to give them all of their bandwidth all of the time. Make sense? Now that's probably not a problem because chances are AT&T has far more bandwidth than they have promised connections to users, just because the maximum speed of the connections is so slow, relatively speaking. All right, so DSL is how this is our modern day version of dial-up, using the exact same connections. It's the exact same situation as this. But instead of modems, we use a DSL modem that sends digital signal over this copper line instead of an analog signal. That's why you don't have any beeping. When Ani gets on the internet, there's no beeping. Oh, you can use the phone as well. Oh, yeah, man. Remember that with the dial-up? Maybe in the middle of a game or something, my mom goes to make a phone call, starts dialing. You messed it all up. Why did it mess it up? Well, it can no longer transfer stuff without errors. His mom's banging on the keys. So then we get the second phone line. Right? The second phone lines are expensive. Even today, isn't it funny how landlines are still expensive today? Nobody uses a landline. Yeah, it comes with your cable provider or whatever, right?
You don't even have them, you just pay for one.
Yeah, it was part of your bundle. Yeah, you get TV, internet, and phone. That's the bundle.
I wish we had
It's like cheaper than just getting.
We do. Our parents still have one. Like within the last 3 years, I think.
Yeah.
I don't think we'd pay for it though.
Right. Well, that's the thing. It's bundled in, so it ends up being free. What he was saying is if they didn't get the package that had all three, they would actually probably pay more for two things. Yeah. Okay. How do we get off on this? How do we get?
Chapter. Talking about
We're talking about
timing.
analog and digital. Yeah, timing.
Oh yeah, the timing thing. All right, because the analogs. This is actually was related, and I just connected it back to some history stuff. So the analog thing is where digital is where we have a signal during a period of time, and that's where the timing charts come in. So because usually we have some sort of electricity powering our devices, right? And those guys might be on some sort of cycle. One of the things when we get to, I don't know what the MIPS timing cycle is on. I don't, they were probably, 8 megahertz processors or something like that. But there's going to be kind of a system clock that cycles on the, this is when electricity pumps through the system. Same thing will be true for any of your combinational circuits or something like that. So we have this timing diagram where whenever it's a low line here, that's off. Whenever it's a high line, that's on. And this transition here is not measurable. You don't get to play in the middle. You don't get a half on thing. Unless you get into quantum computing, which is what me and Mr. Gonzalez are dabbling with our teleporter. But then you have, well, no, you have 3 bits. They're called qubits. You have on, off, or spin, where it's both on and off. Let's not talk about quantum computing in here today. I haven't put my 10,000 hours, but I'm close to that one. We should teach a class on quantum computing. Wouldn't that be fun?
Can we have a model?
I mean, Google's coming out with a language for quantum programming. It'd be awesome. Yeah, I mean, quantum is effectively, instead of on-off, it's on-off spin. We have 3 states. And then you got to figure out what does that mean for everything. Okay, so timing diagrams, you just look at these and it says during this time period, so at the top here, you'd probably have, time period A, B, C, something like that. However they put it on a grid. We'll see what they do in a second here. But during this time period, it's on, or it's off rather. During this time period, it's on. Off, on. For this one, for the first 2 time periods, it's off. For the next 2 time periods, it's on, so on and so forth. So they kind of labeled A, B, and C here. So they would ask, during time period A, what are our variables doing? So during time period A, J is on, K is off. And then, they want you to complete it based on what, a formula? Oh, whatever. Oh, for logic gates, not and or. Yeah, so you would get the outputs outright. So this is a J, this is an OR. So J or K. If for A here, J is on, K is off, Y would be on. So this would be a 1. That makes sense? Because we're applying the OR circuit, the OR gate to this time period A. So this is a 1 or 0. 1 or 0 is a 1. For this one, this is a 1 or 1, which is a 1. This one is a 0 or 0, which is a 0. Make sense? So that's the timing things. They are kind of showing you how to imagine it'll usually be a combinational circuit, but they're showing a very simple, just an OR gate, over a period of time based on what maybe the current electricity flow is. Just giving you an example of reading timing charts. Okay, questions about that? All right, registers. We probably need a break. All right, let's take 5 minutes, 8 minutes, take 8 minutes. So I want a little...
Go for it.